Welcome to Generative AI Futures, brought to you by ByteGoose AI.
We are launching into a truly technical deep dive today, and this one is tailored specifically for you, the technically curious learner. We're assuming you're ready to move past the headlines and really understand the complex, constantly evolving landscape of large language model fine-tuning methodology.
That is precisely the mission. We're moving far beyond just knowing that fine-tuning exists. Today, we're unpacking the specific architectures, the necessary mathematical underpinnings, and the detailed seven-stage pipeline that the cutting-edge AI research community is focused on right now, to make these massive models actually useful and specialized.
And the central theme throughout this entire discussion is really efficiency meets specialization. Fine-tuning is that process that allows a massive, generally knowledgeable model think a foundational llama or a GPT model to be transformed.
Into a specialized instrument.
Exactly, a finely specialized instrument for a specific niche task or domain. And crucially, this practice saves, orders of magnitude in time, data, and computation compared to attempting to train that foundational model from scratch.
Which is still a monumental, almost nation-state level effort.
Oh, absolutely.
And before we get into the nuts and bolts of the fine-tuning process itself, it's probably worth grounding ourselves, just briefly, in the history. We've seen this phenomenal progression in less than 30 years.
It's incredible. It started, and believe it or not, with simple statistics. Back in the 1990s, we had what were called statistical language models, or SLMs, built on n-grams.
Right.
These models were, let's say, rudimentary. They estimated the probability of the next word based purely on the count of the previous one or two words. They were computationally cheap, but structurally incapable of capturing long-range dependencies or, any complex semantics.
The real breakthrough, then, came with that transition to neural language models, the NLMs.
Yes. This is where word vectors, like words to vec, really entered the scene. It allowed computers to understand relationships between words based on context, moving way past just simple frequency counts. NLMs use neural layers to predict sequences, and that suddenly gave the model a much richer semantic understanding of language.
And that evolved pretty quickly into pre-trained language models, PLMs.
Yeah.
This is where we start to see names we recognize, like the early BERT and GPT-2 models.
And that defined the paradigm we still use today. Pre-training on a huge general corpus of text, and then following that with fine-tuning for specific downstream tasks.
Which brings us to the modern era, large language models, LLMs. The defining feature here, of course, is the transformer architecture and its revolutionary self-attention mechanism.
Right, which lets the model simultaneously weigh the importance of all other words in a sequence when it's just processing a single word. This capability unlocked training on massive corpora with billions of parameters.
And that led to the general intelligence we see today.
The transformer's ability to handle those long-range dependencies efficiently is, I would argue, the single technical advance that made modern LLM fine-tuning even possible at this kind of scale.
So when we talk about adjusting these giant pre-trained models, the adjustment process itself falls into a few distinct categories, right?
It does. We categorize fine-tuning primarily by the data you use. So we have unsupervised fine-tuning, which is typically used for domain adaptation on unlabeled data. Then there's supervised fine-tuning, or SFT, where we use labeled input-output pairs to teach a very specific skill.
And instruction fine-tuning.
And finally, instruction fine-tuning, which is really just a specialized form of SFT where the data is structured as instructions to teach the model how to follow commands reliably.
That diversity really highlights just how sophisticated this field is. We're going to spend the next stretch navigating the entire seven-stage fine-tuning pipeline. And we'll culminate in some deep dives into resource efficiency techniques like PEFT, understanding the crucial math behind optimizers, and dissecting the subtle war of attrition between PPO and DPO for model alignment. Before we dive into the technical mechanics of actually updating model weights, we have to address this foundational choice that every development team faces. Should we even fine-tune this model, or is Retrieval-Augmented Generation, RJ, the more appropriate solution?
This decision really dictates the entire scope of the project. REG is incredibly powerful because it's a cost-effective way to integrate proprietary, external, or highly dynamic data without touching the core weights of the LLM.
So you're essentially just beefing up the prompt you send to the LLM.
You're augmenting it exactly, with context that you've retrieved from an external knowledge source.
So give me a real-world scenario. Where is REG the undisputed winner?
Okay, imagine you manage an AI chatbot for a large financial firm. This chatbot needs to answer employee questions using the latest compliance documents, which, let's say, get updated every single week.
Coy.
If you fine-tuned the model with this compliance data, the moment that data changed, your model would be out of date. It would be hallucinating inaccurate information. RG, however, involves indexing those external documents in a vector database. So when a query comes in, the system retrieves the 4 or 5 most relevant document chunks and just passes them to the LLM as context.
So RE excels when the knowledge source is external, or it's frequently updated, or it's just massive in volume. It keeps the LLM honest and up to date.
Precisely. The RG pipeline is very efficient.
Yep.
You process the query, search the vector index, retrieve and rank the context, and then augment the final prompt. It's excellent for Q&A, summarization based on external docs, and dynamic data access.
So if RG handles that dynamic knowledge so well, when does fine-tuning become the mandatory, non-negotiable choice?
Fine-tuning is required when you need to fundamentally alter the model's behavior, its tone, or its internal representation of domain-specific knowledge. You aren't just updating its knowledge base, you are changing its personality.
That's a great way to put it.
So if you need your model to shift from standard conversational English to, say, a highly formal, precise, legalistic writing style, RAG cannot achieve that. You have to fine-tune the weights themselves using a specialized corpus of legal documents structured for that tone.
That's a critical distinction.
Yeah.
So RAG adjusts what the model says by providing context, but fine-tuning adjusts how the model thinks, behaves, and generates language.
And there's another major factor, transparency. One of RAG's greatest benefits is that it inherently provides source attribution. It can tell the user, I retrieved this answer from document A, page 3.
Which a fine-tuned model can't really do.
Not in the same way. A solely fine-tuned model, while highly tailored, typically lacks this direct interpretability or attribution back to a source document that's, buried somewhere in its weights.
Okay, so with that boundary established, let's assume our goal requires altering the model's core behavior or deeply embedding some specific domain expertise. We choose fine-tuning. Let's look at the full life cycle. This isn't just a one-step process. It's a rigorous, structured, 7-stage pipeline.
That's right. Think of it as manufacturing a highly specific intellectual tool. It's a comprehensive life cycle. Stage 1 is data preparation. This is the foundation, involving meticulous collection, cleaning, formatting, and annotation. Stage 2, model initialization. That's selecting the base LLM and handling the initial and often very difficult resource challenge of just loading it.
Then we have stage 3, the training environment setup.
Right. Defining the hardware, the software stack, and selecting the optimal algorithms for adaptation, primarily the optimizer and the hyperparameters.
And stage 4 is the actual work.
Stage 4 is fine-tuning itself, either partial or full. And increasingly, this relies on resource-efficient techniques like PEFT.
After that comes stage 5, evaluation and validation.
Yep. Assessing performance, using advanced metrics and standard benchmarks to make sure the model generalizes properly.
Stage 6 is deployment.
Optimizing the fine-tuned model for fast and efficient inference in a production environment.
And finally, stage 7.
Monitoring and maintenance. This is the continuous phase of tracking real-world performance, addressing any performance drift, and iteratively updating the model over time.
This structure is clear, but we've really got to unpack the complexity hidden in those first 3 technical stages. I mean, that's where the high-level engineering and the mathematics really dictate success or failure.
Absolutely. Data is destiny and fine-tuning. Stage 1 is all about engineering the input that will give the LLM its new specialized identity.
And data ingestion today means dealing with a massive diversity of formats. It requires specialized tooling. It's not just loading a single CSV file anymore, is it?
Oh, far from it. A modern fine-tuning pipeline might simultaneously pull structured data from files using pandas, scrape web pages using libraries like Beautiful Soup and Requests, query complex relational databases with Squall Alchemy, and extract vast object storage from AWS S3 using Bodo 3. This is data engineering complexity at its peak.
And once you collect all that data, it's almost certainly messy. It's going to require significant pre-processing before you can even think about tokenizing it.
It's mandatory cleaning. We rely on traditional NLP libraries like Spacey and NLTK for normalization, handling stop words, basic tokenization. But the most critical step is integrating the task-specific tokenizers provided by the Hugging Face Transformers library.
To make sure it matches the original model.
Exactly, to ensure the new data is segmented exactly how the pre-trained model expects it.
Let's move to one of the most serious, yet I think frequently ignored technical challenges: handling data imbalance. This seems particularly relevant for tasks like anomaly detection or, say, fraud classification.
This is a crucial technical hurdle that standard training often just fails at. If you're training a model to detect fraud and 99.5% of your samples are benign transactions, the model learns a very simple and destructive lesson.
Just say benign every time.
Just predict benign every time, and you'll achieve 99.5% accuracy, but you will fail entirely at the actual task you were hired to do.
So how do researchers combat this fundamental bias in the training data?
Well, we start with data-level interventions. We use the imbalanced learn library for techniques like oversampling, something like SEMOT, which stands for Synthetic Minority Oversampling Technique, creates synthetic data points for that rare class to balance out the distribution.
And the opposite would be undersampling.
Conversely, undersampling removes examples from the majority class. But these techniques often don't go far enough and can sometimes introduce, synthetic noise into the data.
So this is where the math has to intervene directly in the training process through the loss function. Tell us about focal loss.
Focal loss is really elegant in its purpose. It's a modification of the standard cross-entropy loss function. Standard cross-entropy treats all mistakes equally. Focal loss introduces a modulating factor that reduces the weight of the loss contribution from easy examples.
The 99.5% of benign transactions.
Exactly. The ones that the model is already correctly classifying with high confidence.
So it's not penalizing the model less for mistakes on the easy stuff. That seems counterintuitive.
No, that's a great point. It's actually encouraging the model to ignore the correctly classified easy stuff. By downweighting the loss contribution from those easy, high-confidence samples, the model is forced to concentrate its finite learning capacity, its gradient updates on the truly difficult, critical samples.
Which are often the rare ones, the hard negatives or the minority class instances.
Exactly. This is vital for achieving high recall on critical tasks. If you're only optimizing for average loss, you will miss the rare events.
That's a massive conceptual shift. You're essentially teaching the model to prioritize complex, rare examples over simple, common ones.
It's focusing the energy of the optimizer where it matters most. And because of this imbalance, your evaluation metrics have to be tailored. Simple accuracy is meaningless. We have to rely on metrics like precision recall AUC or the F1 score, which provide a more balanced view of performance on both the majority and minority classes.
And beyond just correcting data, we also focus heavily on generating it through augmentation and annotation.
Annotation, which is just labeling the data, is often the biggest bottleneck. We use human annotators for high-quality but very expensive labels, but researchers are increasingly turning to semi-automatic methods like Snorkel, which uses programmatic weak supervision rules to quickly generate initial labels, which can then be refined.
And the augmentation techniques themselves are getting pretty aggressive.
Oh, absolutely. We're moving way past simple synonym replacement. We have techniques like back translation, where you translate your source text, say, from English to French, and then back to English to generate a semantically equivalent but syntactically distinct paraphrase.
That's clever.
We even use adversarial attacks with frameworks like text attack to subtly modify input text to intentionally confuse the model, and then you train the model to be robust against those subtle changes, creating stronger, more generalized training samples.
And the real cutting edge of stage one, using the large language models themselves to generate synthetic data.
This is the meta-level trick, isn't it? Using an LLM via clever prompt engineering and multi-step refinement pipelines to generate massive high-quality, task-specific synthetic datasets. If the model can generate a perfect example of what a good legal summary looks like, well, that generated data becomes the gold standard for further fine-tuning.
Okay, so our data is ready. Now we move to stage two, model initialization.
Stage 2 involves selecting the base LLM, maybe it's LAME 38B or Mistral 7B based on the task and your available resources, and then configuring the environment and loading that colossal weight matrix into memory.
The primary tooling here is pretty straightforward. PyTorch or TensorFlow is the backbone. But the central piece is Hugging Face's Transformers library. It gives us classes like AutoModel for Causal LM to painlessly load pre-trained models.
But while the tools make the loading part easy, they don't solve the immediate resource constraints challenge. This is the hard reality check. Just loading a model like Llama 38B simply to run inference requires a minimum of 16 GB of GPU memory.
And for fine-tuning, it's way more.
Exponentially more, especially for full fine-tuning.
So why the enormous memory jump for fine-tuning? What's going on under the hood?
When you fine-tune, you need memory not just for the model weights themselves. You also need to store the intermediate activations during the forward pass, all the gradients calculated during the backward pass, and the optimizer states. Standard optimization algorithms like AtomW require storing 2 copies of parameters, the momentum and variance estimates, for every single trainable parameter.
So for a 7 billion parameter model.
In 32-bit precision, that memory footprint can easily exceed 100 GB. This fact alone dictated the absolute necessity of techniques like PEFT, which we'll get to in a bit.
Okay, so we've navigated the data and the memory challenge. Stage 3 is the engineering and mathematical core, defining how the model learns by setting up the environment, the hyperparameters, and most importantly, the optimizer.
We're talking specialized compute power now. Fine-tuning these behemoths requires high-end NVIDIA A100 or V100 GPUs or specialized TPUs, and they need to be supported by the essential software stack. CUDA for parallel processing, and CUDN for deep neural network acceleration.
And if your model is too big for even one A100, which many are,
then you have to implement distributed training. You're either using model parallelism, which is splitting the model itself across devices, or data parallelism, splitting the batch across devices.
Now let's define the big 3 hyperparameters that modulate the entire learning process.
Right, the hyperparameters are the tuning knobs of learning. First, you have the learning rate. This is arguably the most important one. It determines the step size the optimizer takes down the loss surface.
Too big and you bounce around, too small and you never get there.
Exactly. Too large, you oscillate wildly, never settling in the minimum. Too small, and training takes geological epochs. Second is batch size, the number of data samples processed before a weight update occurs. A large batch size provides a more stable estimate of the true gradient or requires massive memory. A small batch is memory efficient but leads to noisy, highly variable updates.
And third is epochs.
Just the total number of full passes through the entire training dataset.
Given how interconnected these are, manually searching for the best combinations seems impractical. So we automate the search.
We use automated hyperparameter tuning methods. Grid search is the simplest. You define a grid of values, say a few learning rates and a few batch sizes, and you evaluate every single combination. It's systematic but prohibitive for LLMs due to the massive cost of each training run.
So what's more efficient?
Random search is surprisingly more efficient. It just samples combinations randomly and tends to discover good solutions faster in high-dimensional spaces.
But the most sophisticated approach, the one used by top research teams, is Bayesian optimization.
Bayesian optimization is intelligent search. It treats the hyperparameter space as a function to be maximized like validation accuracy, and it uses a probabilistic model, often a Gaussian process, to predict the performance of unseen combinations. It prioritizes testing parameters that are either predicted to be very good, which is exploitation, or parameters whose performance is highly uncertain, which is exploration.
It's efficient, but sounds complex to set up.
It is. The initial setup and maintenance of that probabilistic model adds complexity.
Okay, now for the calculus of adaptation. The optimizers. This is the technical heart of stage 3. Let's trace the evolution from the basics up to the current standard, AtomW.
The foundational algorithm is gradient descent, GD. It calculates the gradient, the slope of the loss function, using the entire dataset before it updates the weights. It guarantees convergence, but for models trained on trillions of tokens, it's computationally impossible.
Right. So we make compromises to gain speed.
That brings us to stochastic gradient descent, SGD. SGD updates the parameters using the gradient calculated from just one data point, or a tiny handful. This drastically speeds up training and makes online learning feasible, but the updates are super noisy, leading to instability in the loss curve.
So the middle ground is mini-batch.
The compromise and the common practice for LLMs is mini-batch gradient descent, which calculates the gradient over small batches like 8 or 16 samples. It strikes that necessary balance between stable updates and computational efficiency.
But the major historical limitation of all these methods was the fixed learning rate, one speed for all parameters.
Exactly. And this led to adaptive methods, which dynamically adjust the learning rate for each individual parameter. AdaGrad, or adaptive gradient algorithm, was revolutionary because it accumulated the square of historical gradients. Parameters that got frequent, large updates, like common words and text, would see their learning rate decrease quickly, while parameters for sparse features, like rare words, would keep a higher learning rate.
What was the flaw there?
The flaw was that the accumulated gradient eventually caused the learning rate to shrink to almost zero, which stopped learning prematurely. RMSprop, or root mean square propagation, fixed this by using a moving average of squared gradients instead of accumulating the entire history. This prevents the learning rate from diminishing too quickly.
And these adaptive methods culminate in ADAM.
ADAM, Adaptive Moment Estimation, combines the best features. It calculates exponentially decaying averages of both the past gradients, which is like momentum, and the past squared gradients, which is like RMSprop. It's robust, it's fast, and it became the default for almost all deep learning tasks because of its rapid convergence.
So if ADAM was so good, why did researchers create ADAM-W? What does that single letter W signify, and why is it pretty much mandatory for LLM fine-tuning?
This is a deep technical nugget. The W stands for weight decay. Historically, standard ADAM had a coupling issue. It mixed L2 regularization, a technique to prevent overfitting by penalizing large weights directly into the adaptive learning rate calculation.
Hold on, why is combining L2 regularization and the learning rate calculation so damaging to an LLM's ability to generalize?
Because L2 regularization should specifically penalize large weights to keep the model from just memorizing the training data. When standard ADAM performed this L2 weight decay after normalizing by the adaptive learning rate, it disproportionately weakened the regularization effect on parameters that had large historical gradients.
So the regularization wasn't working properly.
It was ineffective, leading to significant overfitting, a huge problem in models with billions of parameters. ADAM-W technically solves this by decoupling L2 regularization, which is now correctly termed weight decay, and applying it outside of the adaptive gradient update step.
I see. The decoupling ensures that the weight decay mechanism, the thing that fights overfitting, is applied uniformly and correctly, regardless of a parameter's past gradient history. It's a subtle mathematical refinement that drastically improves the stability and generalization ability of these massive models.
Exactly. ADAM-W is the standard because it ensures generalization by allowing precise control over weight decay while still retaining ADAM's fast convergence. This complex setup is what makes Stage 4, the actual fine-tuning, possible.
Stage 4 is the training loop itself. And if Stage 3 was about optimization math, Stage 4 is all about architectural efficiency. We have to talk about parameter-efficient fine-tuning, or PEFT.
PEFT is really the indispensable architectural approach, and it's driven by the practical limitations of modern LLMs. As we establish, full fine-tuning a 7 billion parameter model in full precision requires over 100 gigabytes of GPU memory. That puts it out of reach for most research labs. PEFT solves this by mitigating two major issues: catastrophic forgetting of pre-trained knowledge and that prohibitive cost and memory requirement.
The core idea of PEFT is freezing the vast majority of the pre-trained weights and only training a tiny fraction of new specialized parameters. And the reigning champion of PEFT is low-rank adaptation, or LoRA.
LoRA is a brilliant hack. In full fine-tuning, you update the massive pre-trained weight matrix, which we'll call $. LoRA posits that the change required in that matrix, delta WA, can be effectively approximated by multiplying two much smaller matrices by $and dollars.
So instead of updating $2, which might be a 496 by 4096 matrix, we freeze it, and instead we train two smaller matrices, say 4096 by and 30 by 4096 dollars, where $2 is that low-rank hyperparameter.
Precisely. And if that rank $3 is something small, like 8 or 16, the number of trainable parameters just drops exponentially. This means the memory footprint for gradients and optimizer states is tiny, the training is lightning fast, and the storage cost is minimal. You only have to store the small LoRA matrices of by and dollars as adapters, which you can swap out quickly.
That's the first huge leap in efficiency. But researchers immediately push this to the extreme with QLoRA, quantized LoRA.
QLoRA is one of the most significant practical breakthroughs in recent LLM history. It fuses that LoRA mechanism with 4-bit quantization. In QLoRA, the massive pre-trained model is frozen and stored in ultra-low 4-bit precision. But here's the trick. The gradients are still backpropagated through this 4-bit model and used to update the small LoRA adapter matrices, which are stored in 16-bit precision.
That's genuinely mind-boggling optimization. What's the ultimate memory saving?
The source data highlights a staggering result. QLoRA reduces storage requirements from the traditional 96 bits per parameter, that's 32-bit weights plus 32-bit momentum plus 32-bit variance estimates, down to just 5.2 bits per parameter.
An 18-fold reduction.
It's an 18-fold reduction, which fundamentally changed the accessibility of fine-tuning large models. It enabled high-quality fine-tuning on consumer-grade hardware or a single research GPU in a matter of hours.
It sounds like the equivalent of compressing a massive digital library down to a single flash drive without losing any of the underlying knowledge structure. That's a triumph of algorithmic engineering.
And the research doesn't stop there. We have refinements like weight-decompose low-rank adaptation, or DoRA. DoRA suggests that the delta W update should focus specifically on the directional changes, separating the weight matrix into magnitude and directional components. By applying the low-rank approximation, the B times A, only to the direction, DoRA aims to achieve learning outcomes much closer to full fine-tuning.
And it often surpasses standard LoRa performance.
Often, yes, while maintaining all the efficiency gains.
Moving outside the low-rank family, let's talk about half fine-tuning, or HFT. This seems less about compression and more about strategic knowledge retention.
That's exactly right. HFT uses a different approach to parameter selection. Instead of inserting small new matrices, HFT strategically freezes and updates existing parameters within the repetitive blocks of the transformer architecture, the self-attention layer, the feed-forward network, and the layer normalization.
So what's the mechanism?
The mechanism dictates that in each block, half of the parameters are frozen and half are updated during a training pass.
How does that compare conceptually to LoRa?
LoRA is an efficiency play. It's all about compressing the update using new low-rank matrices. HFT, on the other hand, is a knowledge play. By updating only half the parameters in the pre-trained structure, HFT excels at balancing the retention of the model's vast foundational knowledge, which lives in the frozen weights, with the necessary acquisition of new task-specific skills.
So it's a selective surgical update, whereas LoRa is more like an efficient prosthetic insertion.
That's a great analogy.
The idea specialization is clearly driving all these architectural decisions, which leads us naturally to the sparse architectures like mixture of experts or MoE.
MoE is perhaps the most exciting architectural shift of the last couple of years. It treats the LLM not as one giant monolithic system, but as a collaboration of specialized subnetworks, which we call experts. It's a sparse activation architecture. For any given input token, a small router network or a gating network decides which subset of these experts should actually process the token.
So the model might have, say, 100 billion total parameters, but during inference for just one token, it only activates maybe 20 billion of them.
That is the core technical magic. The computation is divided, allowing the model to dramatically scale its total capacity, its number of parameters, without inflating the computational cost during inference. The most famous example of this is Mixtral 8x7b.
Unpack that mixtral number for us.
Mixtral 8x7b actually holds 47 billion parameters in its total capacity. But because of its MoE design, for any given token, the router selects only 2 of its 8 experts to be active. This means that during inference, only 13 billion parameters are actively used per token.
So you get the knowledge capacity of a much larger model, but with the speed and inference cost of a 13 billion parameter model.
It's a complete game changer for production deployment.
And the evolution of that concept leads us to this non-weight-based specialization approach, the mixture of agents, or MoE.
MoE moves the specialization from the internal weight architecture to the external model level, and it operates through prompt-based interaction. So instead of having internal expert subnetworks, MoE uses multiple full-fledged separate LLMs, each acting as an agent with a specific role.
How does this ensemble of LLMs generate a single response?
They collaborate through assigned roles. You have several proposers, which are diverse LLMs generating initial draft responses or reference answers based on the prompt. Then a final aggregator agent merges and refines these diverse proposals into a single, high-quality final output.
What's the key technical insight there that makes MoE better than just using the best single LLM?
The research shows that the aggregation step, the merging of diverse outputs, is superior to simply selecting the best single response. And the performance gain is tied directly to the diversity of the models you use. Using 5 different types of LLMs as proposers yields better results than using 5 instances of the exact same LLM.
Suggesting that variance in perspective is a critical driver of quality.
Exactly.
This theme of modularity and specialization carries through to the use of multiple adapters, which allows a single LLM to handle diverse tasks.
Yes. Using the PEFT library, a developer can fine-tune separate LoRa adapters, say one trained for code generation and another for creative writing on the same base model. The crucial step comes when you want that single base model to do both tasks seamlessly. The library lets you merge these specialized adapters into a single, unified multitask adapter.
And how is that merging operation mathematically executed?
Well, the PEFT library offers options. You can use simple concatenation, where the resulting adapter matrix just has a higher rank. You could use linear combination, which is a weighted sum of the parameters, allowing you to prioritize one task over another by setting a higher weight. Or there's the more advanced SVD, singular value decomposition, which attempts to find a lower rank approximation of the combined knowledge.
Which makes the LLM highly flexible without needing expensive retraining cycles.
Absolutely. You can combine skills on the fly. So we've optimized for efficiency through PEFT. Now we face a completely different challenge. Alignment. I mean, efficiency means nothing if the LLM is factually wrong or generates harmful content. We need to ensure the model aligns with explicit human preferences and safety guidelines.
And this brings us to the evolution of reinforcement learning from human feedback, or RLHF. The classic method, which is highly complex, is Proximal Policy Optimization, or PPO.
PPO is an elegant but very intricate process. It involves multiple moving parts. Its mechanism requires the creation of a distinct reward model. This reward model is first trained on human preference data, where humans have ranked or compared different responses to the same prompt.
So it learns what humans like.
It learns to output a scalar score, a reward, estimating how much a human would prefer a given response.
So the reward model is basically the LLM's conscience.
That's a perfect way to put it. PPO then uses this conscience. The main LLM, the policy, is trained using the reward signal from the reward model to maximize its expected cumulative reward. Technically, PPO uses policy gradient methods with a crucial addition, a clipping mechanism in the objective function. This clipping limits the size of policy updates in each training step, which is vital for maintaining stability.
To stop it from going off the rails.
Right. It prevents the model from drastically changing its behavior too quickly, which is a constant risk in RL training.
PPO sounds incredibly difficult to manage. You're training two models, you're dealing with the instability inherent in reinforcement learning, and you have to fine-tune that reward mechanism. This naturally led to the search for a simpler method, which is Direct Preference Optimization, or DPO.
DPO is a breath of fresh air because it entirely simplifies the pipeline. It completely eliminates the complex step of training and managing that separate reward model. Instead, DPO directly optimizes the LLM using a simple classification objective based solely on the human preference data.
The pairs of preferred versus rejected responses.
Exactly.
So instead of maximizing some predicted reward, DPO just maximizes the probability of generating the preferred response relative to the rejected one.
That's the simplest way to put it. It turns the complex reinforcement learning problem into a much more stable and easy to implement classification or log likelihood maximization problem. The setup is cleaner, more stable, and frankly, less computationally demanding to implement.
Wait, if DPO is so much simpler, it only requires one training loop and avoids the instability of the reward model, why hasn't PPO simply been retired? Where does DPO fall short that PPO still wins?
That's the crux of the current research debate. While DPO's simplicity is incredibly appealing, studies suggest it comes with a potential trade-off in robustness and ceiling performance. A comprehensive analysis showed that PPO, when it's highly tuned with advanced techniques, especially using large batch sizes and key normalization methods like advantage normalization, can actually achieve superior results in highly challenging zero-shot domains.
Like complex code generation.
Exactly. For example, the code contest dataset.
So DPO is the great generalist, but PPO, when it's expertly handled, is still the domain specialist for those highly difficult tasks.
That's a fair summary for now. Furthermore, some theoretical findings suggest DPO may yield biased solutions, particularly by exploiting out-of-distribution responses in the preference data. Its effectiveness is highly sensitive to the quality and distribution of that human preference data. PPO, despite its complexity, offers greater control over the exploration-exploitation balance via the reward function, which is critical in certain difficult domains. The battleground for high-fidelity alignment is still very much active between these two methods.
Moving from the alignment techniques to validation, Stage 5 is all about quantification. We need to ensure that the complex optimization we just performed actually led to a better, more generalized model.
And the starting point, the workhorse metric for training, is cross-entropy. As the loss function, it provides the fundamental measure of error during training. It's calculating the difference between the model's predicted probability distribution over the vocabulary and the actual ground truth distribution. Minimizing this is the primary goal of all those gradient descent steps.
But relying only on cross-entropy or simple accuracy is just not sufficient for judging a modern LLM's utility, is it? We need metrics that
Yeah.
capture nuance like hallucination or relevance.
Oh, we absolutely need advanced metrics. Key performance indicators for LLMs include perplexity, which is a measure of how well the model predicts a sequence. Lower perplexity means the model is more confident in its language modeling capability.
And factuality.
Factuality, which is crucial for knowledge-based applications, assessing the accuracy of generated information. Then you have context relevance and completeness, especially critical if we've combined fine-tuning with RAG principles. This measures how relevant the model's output is to the original query and whether it addresses all the components of the prompt.
What about chunk attribution?
Chunk attribution is a specialized metric to evaluate how successfully and accurately the model used the specific retrieved information chunks to construct its final answer. It ensures the output is grounded in the provided context.
During the training process, the primary diagnostic tool is the training loss curve. What patterns do we look for when we're monitoring this?
Interpreting the loss curve is vital for real-time diagnosis. If both the training loss and the validation loss are high and flat, the model is underfitting. It hasn't learned the basic patterns of the data. Maybe the learning rate is too low or the model is too simple.
And the classic sign of failure.
The classic sign of failure is when the training loss continues to decrease, but the validation loss starts to increase. This indicates overfitting. The model is just memorizing the specific idiosyncrasies of the training data, but failing to generalize to new, unseen examples.
And when overfitting happens, that's when we rely on the techniques we set up back in stage 3. Using dropout, leveraging that weight decay which Adam W. correctly decoupled, and potentially early stopping to terminate training before the validation loss climbs too high.
And to truly gauge generalized ability, we have to submit the fine-tuned model to standardized stress tests.
The benchmarks.
Precisely. We assess against standard benchmark suites. Things like MMLU, which tests academic knowledge across 57 subjects, Truthful QA, which measures the model's propensity to generate false answers, challenging its resistance to hallucination.
And the classics like HelloSwag and SuperGeoUE.
Right. Standard tests for common sense reasoning and general NLP capabilities. And increasingly important, IEVAL, which tests the model's ability to follow complex multi-step instructions reliably.
Finally, we must ensure the model is safe. Safety benchmarking is a technical requirement, not just an ethical afterthought.
Absolutely. Safety benchmarking evaluates the model against metrics like toxicity, stereotype bias, and adversarial robustness. This often involves using specialized, safety-focused LLMs to evaluate our fine-tuned model. For example, LlamaGuard 3, which is itself a fine-tuned Llama 3.8b model, or Shield Gemma, are used as automated AI moderators. They classify prompts and responses based on a detailed risk taxonomy, covering everything from harassment to criminal planning.
To ensure our specialized model adheres to the required guardrails.
Exactly.
Before sending the model off to deployment, we can further optimize its size using pruning operations.
Pruning is like the digital liposuction of deep learning. The goal is to eliminate redundant parameters to reduce size and complexity for faster inference without significant performance loss. We have weight pruning, which removes connections whose weights have minimal magnitude, unit pruning, which eliminates entire neurons or attention heads, and filter pruning, which is common in convolutional networks.
And the Holy Grail.
The Holy Grail is dynamic pruning, which adjusts the network structure on the fly during inference, optimizing the model for the specific hardware it's running on.
Stage 6 is the transition to production, where theoretical efficiency must translate into real-world speed and cost savings. The first infrastructure decision is always cloud versus self-hosting.
It's a classic trade-off. Cloud-based solutions like AWS Bedrock offer simplified access and token-based pricing, which is great for low-volume, elastic workloads. However, self-hosting requires a high upfront hardware investment. We're talking server racks full of NVIDIA GPUs, but it provides superior privacy, total control, and significant long-term cost savings for high-volume, consistent usage.
For organizations that want streamlined fine-tuning without building all that infrastructure from scratch, industrial platforms have matured significantly.
They have. These platforms bridge the gap by providing integrated tooling. On the Hugging Face side, you have AutoTrain, which offers automated, minimal-code fine-tuning for standard tasks, versus the Trainer API, which provides deep control for researchers who want to manipulate the learning loop and add custom callbacks.
And on the AWS side,
AWS offers SageMaker Jumpstart for pre-built, streamlined solutions, and Bedrock provides a unified API for interacting with and fine-tuning a diverse range of foundational models.
and for those running serious GPU farms, NVIDIA has its own specialized solutions.
NVIDIA NeMo Customizer is designed for high control, specializing in integrating deep security guardrails and domain-specific knowledge, and it leverages the high-performance capabilities of the NVIDIA hardware ecosystem.
But the real technical battle in deployment right now is optimizing inference speed and memory. We need to talk about three key architectural innovations that are tackling this.
The need for low-latency, high-throughput inference has spurred incredible innovation. First, there's distributed deployment, sort of a torrent-style approach. This leverages libraries like Petals. Instead of running the massive model on one server, Petals partitions the model's layers across a decentralized network of GPUs.
So when a user sends a prompt, the forward pass happens across multiple machines in parallel.
Exactly. This significantly reduces the financial burden on any single entity and speeds up inference by distributing the computational load.
Second is WebGPU WebLLM.
This is really exciting for privacy. It enables deploying LLMs directly into the user's web browser. By utilizing the client's local GPU, thanks to technologies like WebGPU, you achieve much faster inference and significantly enhanced privacy. Functions like PII filtering or translation can happen locally on the client machine without the sensitive data ever having to leave the device.
And the third one is VLLMs and page attention.
This is a crucial innovation for maximizing throughput, especially in self-hosted scenarios that are serving many users simultaneously. VLLMs uses the page attention algorithm to efficiently manage the key value cache, or KV cache.
And the KV cache is a huge memory bottleneck during inference, right?
It's massive. Every token generated requires storing its key and value vectors, and this cache grows linearly with the length of the sequence, leading to memory fragmentation and waste. Page attention solves this by managing the KV cache in discrete memory blocks, analogous to virtual memory in operating systems. It drastically reduces memory fragmentation, allowing VLLMs to pack more sequences into the same GPU memory, maximizing throughput and reducing the cost per inference.
The techniques we discussed for efficiency and optimization, they all apply to the next great frontier, multimodality.
The moment you introduce vision and language together, you're dealing with a vision language model, VLM. The architecture fundamentally shifts. It requires three components: a specialized image encoder, often a frozen vision transformer, a text encoder, which is our standard LLM backbone, and a fusion strategy, typically another transformer backbone that learns to align the information from the visual embeddings and the textual embeddings into a shared representation space.
So how does fine-tuning address this new complexity?
It requires highly targeted fine-tuning. Let's take the specialized case study of medical visual question answering, or MED-VQA. To achieve this efficiently, researchers usually freeze the memory-intensive vision encoder and the bulk of the pre-trained LLM weights. They apply LoRA, updating only the small LoRA adapters within the LLM backbone, and crucially, updating the specialized linear projection layer that's responsible for mapping the high-dimensional visual embeddings into the LLM's token space.
So we only train the bridge that connects the image data to the language brain, plus the small LoRA adapters for task specialization.
Exactly. This focused fine-tuning achieves high accuracy on complex VQA tasks while maintaining efficiency by not wasting computation on retraining the already expert vision components.
Audio LLMs present a distinct challenge, though, because audio is continuous, unlike text, which is already discrete.
That's the core difficulty. You have to first discretize the continuous audio signal into manageable, high-fidelity audio tokens before the LLM backbone can even process them. Techniques like Hubert or Wave2Vec are used for this specialized acoustic tokenization. Once it's tokenized, the LLM processes the audio stream alongside text, allowing it to operate within a unified, shared, multimodal space for tasks like speech recognition or conversational AI.
Finally, Stage 7 involves monitoring and maintenance, which forces us to confront the persistent, open challenges that define the current research horizon.
And the foundational challenge remains scalability and resource issues. We repeat this because it dictates everything. The sheer memory required upwards of 112 GB of GPU memory just for full fine-tuning. A small 7 billion parameter model makes full fine-tuning impossible for all but the best-funded labs.
That pressure drove PEFT for parameter efficiency. Now we're seeing the emergence of data-efficient fine-tuning, or DEFT.
DEFT is a promising solution that shifts the focus from parameter efficiency to data optimization. The premise is simple. Why train on redundant data? DEFT uses data pruning to intelligently select only the most critical, influential data samples for fine-tuning.
But how do you know which samples are the most influential without training on them first? That sounds like a bit of a chicken and egg problem.
That's where the smart optimization comes in. DEFT uses a smaller, computationally less intensive surrogate model to approximate the influence of each data sample. The small model, which is cheap to run, acts as a filter. It identifies which data points are critical for learning and which are redundant. The expensive, large LLM is then only fine-tuned on this pruned, highly valuable dataset.
That's a brilliant strategy, using a chief scout model to pre-process the data for the expensive main model.
It leads to rapid adaptation and significant cost reduction, making fine-tuning feasible in environments where data volumes are immense, but computational cycles are limited.
The final, ongoing challenge involves the ethical constraints around bias and privacy, which fine-tuning can often amplify if the source data is flawed.
And we have to rely on technical interventions to address these risks. For bias, especially in specialized domains like healthcare, we have to use tools like Google AI's fairness indicators to evaluate performance metrics across different demographic groups and ensure the model isn't performing well for one group but poorly for another.
And since fine-tuned models can inadvertently leak sensitive training data, privacy is a constant technical concern.
To combat leakage, we use highly specialized techniques. Differential privacy adds carefully controlled noise to the data during training to statistically prevent the model from memorizing specific data points. And federated learning addresses privacy by keeping sensitive data localized on client devices. Only the model updates, the gradients are shared, not the raw data itself.
Ensuring privacy is maintained while still allowing collaboration.
Precisely. And of course, there's the underlying security issue. Fine-tuned models can be susceptible to adversarial attacks, which require techniques like adversarial training to build robustness.
Indeed. The final stage of monitoring must include continuous security testing to ensure the specialized model isn't being manipulated in production. We have conducted an exhaustive technical review of the LLM fine-tuning lifecycle, covering everything from that fundamental choice between external knowledge retrieval via RISH and internal weight modification via fine-tuning, through the critical nuances of optimization calculus like AtomW, the revolutionary efficiency gains of QLORI's 5.2 bits per parameter, and the nuance alignment challenges posed by the complexity of PPO versus the simplicity of DPO.
What really stands out is that for the sophisticated learner and researcher, the technical feature is predicated on resource efficiency. PEF, sparse fine-tuning, and the emerging field of DEFT are essential not just for cost reduction, but for making models that are otherwise too large to manage even operable. The core technical battleground remains efficiency, epitomized by LoRA and QLORA versus high-fidelity model alignment.
That relentless focus on specialization and efficiency is driving fundamental architectural shifts, moving away from monolithic designs. We see models like Mixtral using the mixture of experts architecture to dramatically scale capacity while maintaining low inference costs, and LoRA adapters allowing us to merge specific skill sets.
Which brings us to our final provocative thought for you to consider. As specialized components, from tiny LoRA adapters and MoE experts to external MoE agents, become the default essential tools in the AI stack, are we heading toward a future where every LLM is less a single, massive, monolithic brain and more a hyper-efficient network of highly specialized, replaceable, customized parts designed and optimized down to the level of a single task or even a single user?